dimensions of any physical quantity is a power. How did you define pressure? Force per unit area. Length raised to the power 2 is area. Length raised to the power 3 is volume. Any quantity that can be measured is a physical quantity. A physical quantity is some power. Hello students, this is SDsir again from the Temple of Excellence, Vidhyaashram Pre-University College, Mysuru. A new session, a new start, a new dimension. What is that? I tried to reach you all in this session. Dimensions, dimensions, and dimensions. So the entire session is to understand a very trivial but very important topic in the understanding of physics, something called dimensional analysis. We will try to understand what actually does the word dimension mean. We will write dimensional formulas for few physical quantities, and at the end of the session we will understand what is the uses of dimensional analysis. So my first encroachment here is to make you all understand what is a dimension. Now textually your textbook says dimensions of any physical quantity is a power. This is the word I want you all to highlight: power. Dimensions of any physical quantity is a power to which fundamental quantities are raised. I have spoken about fundamental quantities, derived quantities. So power to which fundamental quantities are raised to get back the given physical quantity. Very textual definition. Idenappa idu istond complex agide? Nothing. The moment I give you an object, and if I ask you, my dear students, what are the dimensions of this object? You may say length, breadth, area, volume. Good. With all these things, what is that we are trying to understand? Now, please do know, if you want to write the dimensions, if you want to write the dimensional formula for any physical quantity, you need to know its definition well. See, for example, I will write the dimensional formula for area. Please note, as I have written on the board, dimensional formula is always enclosed within square brackets. Very important. Always dimensional formula for any physical quantity is enclosed within square brackets. Now, suppose area of a rectangle, length into breadth, some length into length, triangle, half base into height, again some length into length. So generally I write area is some length into some length. So this is L into some L, or this is L square. Now observe, dear students, I have written the dimensions for a physical quantity called area. I told any quantity that can be measured is a physical quantity. And what is area equal to? L square, length raised to the power 2. What is length, students? Wasn't it a fundamental quantity? So a fundamental quantity called length raised to the power 2 gives you the dimensions of area. So what are dimensions? Please to understand, dimensions are nothing but powers. They are the powers to which fundamental quantities are raised to get back the given physical quantity. For example, next, volume. You have studied volume is length into breadth into height. Some length into length into length. L cube. See, L raised to the power 3. Length, fundamental quantity called length, which is raised to the power 3, gives me the dimensions of volume. So again, dimensions is nothing but a power. It is power to which a fundamental quantity is raised. Why? To get back the given physical quantity. Therefore, the basic definition of dimensions, no exaggerations, no quantum physics here. It simply says dimensions of any physical quantity is some power. Length raised to the power 2 is area. Length raised to the power 3 is volume. So power to which a fundamental quantity is raised, so that I can get back that physical quantity. Now, if I want to write the dimensions of density, I told if you need to write dimensional formulas, you need to know the definition. So density, my dear students, is mass divided by volume. So dimensions of mass divided by dimensions of volume. Remember always, dimensions of mass is m. There you wrote representation, 7 fundamental quantities. Mass, capital M. From the previous example, volume L cube. That L cube goes to the numerator, L minus 3. So what is the dimensions of density? M, L to the power minus 3. So M to the power 1, L to the power minus 3 gives me the dimension of density. Now how do I write its unit? Very simple. Mass kg. Did we write this unit? Yes. Mass kilograms SI unit. Length meter minus 3. So kg minus meter minus 3 is the unit of density. Next, velocity. All of you have studied this definition in your school. Rate of change of displacement, or we wrote displacement divided by time. You will come to understand higher concepts when I say rate of change. It is a quantity with respect to time. So velocity is displacement divided by time. Note, displacement, distance, length, radius, height, depth, anything with respect to distance will have the dimensions L. So displacement is L, time is t to the power 1. If this t to the power 1 goes to the numerator, t to the power minus 1. Very good. So by heart this, what is the dimensional formula for velocity? Lt minus 1. So what should be its SI unit? Meter second minus 1. So velocity SI unit is meter per second. Acceleration. Sir, I know the formula. What is it? It is rate of change of velocity. Good. Or we say it is velocity divided by time. So, dimensions of acceleration should be dimensions of velocity divided by dimensions of time. Students, what is the dimensions of velocity? It is written earlier, sir. It is Lt minus 1 divided by time t. So it is Lt minus 2. Numeratorally, t minus 1 is already there. This t goes to the numerator. One more t minus 1. Lt minus 2. What is the SI unit? ms minus 2, or meter per second square. Next, dimensional formula for force. Very simple, sir. Our high school teachers have taught from Newton's second law. Force is mass into acceleration. Yes, F into A. What was the dimensional formula for mass? M. Acceleration, we wrote earlier, Lt minus 2. So M, Lt minus 2 for force. Please to understand a very important dimensions for force, which is mass into acceleration. Mass is M, acceleration is Lt minus 2. So put together M, L, T minus 2. What is its SI unit? Mass is kg, meter second minus 2. But for force, we have accepted a unit after the name of a scientist, Newton. So the followed unit for force will be Newton. Momentum. How do we define momentum? Product of mass and velocity. Momentum is always a product. It is the product of mass and velocity. Mass is m, velocity is Lt minus 1. So m Lt minus 1, mass into velocity, m Lt minus 1. Mass is kg, Lt minus 1 meter second minus 1. Similarly, impulse. This is an assignment for you all. I want you all to get me the dimensional formula for impulse. Work. How did you define work? Force into displacement. This is what I told. You need to be smart with your definitions. Work is force into displacement. Force mLt minus 2, displacement L, written earlier. So this L into L is L square. So mL square T minus 2. So work is force into displacement. Dimensional formula for force, mLt minus 2, mass into acceleration. Displacement L, mL square T minus 2, and the accepted unit is joule. SI unit for work is joule. Pressure, force divided by area. How did you define pressure? Force per unit area. So dimensions of force divided by dimensions of area. Force mLt minus 2, area mL square. So mL minus 1 T minus 2. This will give you the dimensions of pressure with unit Pascal. Again, an assignment where you will write the dimensional formula for power. Next, this is a keynote here. I want you all to follow this. Dimensional formula for kinetic energy. For kinetic energy, the dimensional or the definition is half mass into velocity square. Generally, we wrote it is half mv square. Remember, dimensional formula based on definition. Definition for kinetic energy is half mv square, where v is velocity. Now, what is the dimensional formula for half? My dear friends, make it a point thorough in brain. I cannot write the dimensions of a number. Dimensional analysis gives me no information about the dimensions of a number. If there are numbers present in the definition, as you have here, half mv square, I cannot write the dimensions of half. Not only half. Wherever you have a number, the dimensions cannot be written. Therefore, eliminating this, dimensions of mass, m. What was the dimensions of velocity? We know, sir, Lt minus 1, but velocity square, so Lt minus 1 whole square, m. Lt minus 1 whole square. So L square T minus 2, or it is m L square T T minus 2, and the SI unit is joule. So as an inference here, what I am trying to explain is, wherever you have a number, its dimension cannot be written. It is a limitation of the analysis. I cannot write dimensions for a given number. Next, potential energy. Potential energy, basic definition is mgh. Mass, small g, acceleration due to gravity, h, height. So dimensional formula for mass is m, acceleration due to gravity, a term associated with acceleration. So it has the dimensions of acceleration, LT minus 2, height L. So when I solve m L square T minus 2, very interestingly, if you see, either kinetic energy or potential energy, they have the same dimensional formula. So energy in general has the dimensional formula m L square T minus 2. Frequency, reciprocal of time. Time, reciprocal of frequency. So frequency is 1 by time, 1 divided by t, t minus 1, and the SI unit is hertz. So here I have given a few quantities, and based on the definition I have written the dimensional formula. Please do open up your textbook. At the end of the textbook, there are several physical quantities with definition whose dimensional formulas are written. Please go through them, become well versed. Very important to understand this topic. Now, why do I need to write dimensions? What are the uses of dimensional analysis? The first use is to check whether the physical equation is correct or false. Suppose I have an equation of the form V equals U plus AT, V square equals U square plus 2AS. Suppose I am given a physical equation. I have to check whether it is right or wrong. How do I do? It is by employing the method of dimensional analysis. So in my next session, I will take up examples, mathematically work out and show whether the given equations are correct or false. So the first advantage is to check whether the given physical equation is correct or false. Second, to convert a unit from one system to another. Suppose I need to convert a unit from CGS to MKS, CGS to FPS, one system of measurement to another. I use dimensional analysis. Or to derive physical equations involving different physical quantities. So these are the three applications of dimensional analysis. I will take up example by example, work out and show the uses in the next session. Until then, be thorough with the dimensional analysis part to write dimensional formula for different physical quantities. Have a great time. Thank you.